Right, so good evening, everyone, and welcome to the course Electrical or Systems. My name is Mu'tasim Noor. I am the course lecturer, and also I am the global course leader across the university, Edinburgh, Malaysia, and Dubai, including also distance learning as well. So today we will start with an overview introduction about the course. Then after that, we will have an intro or revision about AC circuits. So the contents for today, as you can see on this slide, the aim and course content, what's also its importance to you as an energy or renewable energy engineer. Course assessment, this is important. Of course, you want to know how is the course assessment, coursework, exams, etc. Course engagement and support. What is the expectation from you in order to understand and pass the course with good grades and understanding as well? Course material and timetabling, intro to electrical power system in general. So the aim of this course is, sometimes we call it module. This is known in the UK. Course or module are the same. It will cover operation of interconnected electrical power systems. Such interconnected power system combine a number of different components. We're going to look at the electrical power system entirely. We're going to start from the generators, then after that transmission lines, transformers. We are using transformer to step up, step down, and transmission lines as well. And then we look at the load. What is the load here? We're going to focus on motors. I mean, if we look around, most of the electricity generated is consumed by what? You're living here, for how long you're living in Dubai? 1.5 years. What do you think most of the load, power, is consumed by what? Air conditioning, exactly. You are absolutely correct. Air conditioning, we need a compressor and a motor, induction motor. So basically, I would say about 60 to 70% of the electricity generated is consumed by motors, which are used to drive. Also in industry, go to industry. I mean, in order to actuate systems, we need motors, all right? Majority. I mean, if you look at lights, right, it's not going to be that much. Look at our appliances at home, fridge, washing machine. We have motors, normally induction motors or universal motors, and so on. So majority of the electricity generated is by motors. So that's why we put here motors, and mainly it's going to be induction motor or three-phase induction motor, all right? So we are going to study all of these, all right? And once we finish, we will go to load flow analysis, fault calculations, and finally power equality. So any course, we have learning outcomes, and these learning outcomes must be achieved. So you're going to ask yourself, once you complete this course, did I achieve? You need to come to this first slide and reflect, all right? So that's important. So the outcomes here are the knowledge and understanding of principle, underpinning areas of electricity and magnetism. So look, we are starting from scratch here, assuming that some of you are not from electrical background. So we start with basics. First, we start with AC circuits to understand the fundamentals. Then we move to transformers, power transformers, synchronous generators, induction motor, and transmission line. Then to understand of engineering principle for single and three-phase system, including symmetrical and asymmetrical fault calculation. If there is fault going to happen across our transmission or electrical power system, how to calculate the fault, because normally we need to know what is the fault in order to protect our system. How we protect it? By circuit breakers, switch gear, fuses, and so on. So we'd like to find out what is the fault level, how much current when we have a fault, in order to include in between a circuit breaker Why? When there is a fault, the circuit breaker will trip and open the circuit. So we are protecting our system. So if there is a fault, the circuit breaker will take care, will open the circuit, and no current will be flowing. So the idea of all fault calculation is just to find what is the size of our protecting systems, which includes the circuit breaker, relays, switch gear, and fuses. Normally, these are what we use across the power system. Then understanding of load flow analysis methods and power quality issues. Load flow, we try to find the load flow calculation when there's a power flowing, what is the voltage, the current, etc. Right? So we are going to take you through all of these things. Then comprehensive knowledge and understanding of mathematical computer model for load flow analysis. We'll introduce you to MATLAB. Do you know MATLAB? Yeah, you'll use MATLAB for a coursework, which is simple. I don't anticipate that's difficult, but you need to simulate a load flow problem in order to complement your understanding and achieve the learning outcomes. This is the course content. This everything what we are going to cover, starting from introduction to electrical power system, single phase and three phase AC. So today, hopefully, we'll have a introduction only about single phase, and next week about three phase and power transformers, AC synchronous generator, polyphase induction motor, transmission lines and cables. We'll just follow the simple. We're not going to go in details. All right. Just we take short and medium type transmission lines, system calculations and the per unit method, power system fault calculations, load flow, which is, as we mentioned, and finally the power equality issues. All right. Now, these are important, although it is power system, but if you are studying electrical, if you are studying MSc in energy or MSc in renewable energy engineering, that's very important, because once you generate the electricity either using traditional way, using thermal power stations, or using renewable, you need to integrate them with this power system and then dispatch them to the end user, to the customers, right? So as a renewable energy engineer, it is needed. You need to know this. It's important, right? Any question for the course content? So you have the freedom to ask questions. Don't keep anything in your head if you have doubts or if you have a question, right? Assessment. There are two components in the assessment. Final exam, which is 2 hours, a closed book exam, and coursework assignment, which is 30%. We have components for the coursework. 2 online quizzes, which is 10%. Each one is only 5%. It's going to be entirely online. I'm going to talk about it soon in the following slide. But please check with your local lecturer for the arrangement requirements. I mean, if in other campuses, I think in Malaysia, because we have MNG students, the arrangement will be slightly different. But for us here, it's going to be online. All right. It is time limited. Normally, we give you 1 hour for short questions. The idea is to keep you engaged with the course and practice. Yeah, the percentage is little, 5% for each one. The second is the major one, which is the report assignment on a MATLAB assignment. So more details about this. I mean, let's start with the final exam. This will be timetabled anytime during the December exam date, first weeks of December. So if you look at the exam timetable, it's going to be from 2nd December until 16th December. So anytime, any 2 hours, normally it's going to be in the evening, 5 or 6 p.m., especially so not to affect for those who are working. This is going to be 70% of the course. The exam will be conducted on campus and vigilated in these classes. Although it's a closed book exam, a formula sheet will be provided together with the exam paper. So this is the nice thing about it. We don't want you to memorize formulas, because you will see lots of equations, formulas. Don't memorize them. We're going to give you a data sheet about 20 pages, which covers almost all the equations for all chapters. and we make it available to you during the exam. All right? Just you need to know how to apply, all right, these equations. The exam consists of 4 questions, and students are required to answer any 3 questions, right? So 4 questions. So normally each question will requires about half an hour to 40 minutes, right? Maximum, right? So which is enough for 2 hours. The questions format are divided as below. Question 1 covers the first 5 chapters because these are kind of intro and revision. The question 2, 3, and 5 covers chapter 6 to 10. So if you go chapter 6 to 10, yeah, starting from here, transmission systems until these are going to be 3 questions, and from here to here is going to be 1 question, right? Okay. Past exam paper and formula will be made available on Canvas. Now, if you look, the formula sheet is available. If later when we finish, I'm going to take you through the Canvas page. Right? Online quizzes, 2 online quizzes, each contribute 5% of the course assessment. Total is 10%. This will be available in the assignment section on Canvas. From there, where you can access them. It's time-limited quizzes with 1 attempt, but the quiz will be open for 24 hours. So there is a window, 24 hours. Any 1 hour you feel is comfortable for you, you can go and do it, right? But once you start, you have to complete it. So you can do it and submit online on Canvas at your convenient time. It's the same quiz everywhere, by the way. Is here, Malaysia, Edinburgh, and distance learning, all right? We are making it. The quiz is not, the questions are not necessarily to be the same. We have bank of questions, different numbers, but it's going to be almost the same level of difficulty for all the students. Quiz 1 is scheduled in week 5, and the quiz 2 is scheduled in week 10. Look at the key dates. You will find exactly when it's going to be released. Did you manage to look at the key dates? Not yet? Okay, we'll take you through. Report assignment. This assignment contributes to 20% of the course assessment. The assignment description will be available on Canvas by week 3 or 4. I think look at the key dates, which is available on Canvas. I'm going to show it to you now. You are expected to organize the report in the correct structure, to present the argument correctly, to present figures. The description of the assignment is clearly be available to you, and also what is expected from you as well. The supporting tutorial from YouTube for how to use MATLAB and the power flow will be also available to you on Canvas. So you will have plenty of time to do it. You can again do it at your own time. Normally, if it's going to be released in week 3 or 4, you will submit it in week 11. So you will have, yeah. It should be possible, yeah. It should be possible. Yeah, yeah, it's fine. Yeah, yeah. As long as you provide, I mean, the code in the assignment and get the required results, it's fine. We don't limit you. I mean, yeah, you could use also not necessarily MATLAB, any other tools. We have also ETAB, for example, to do the same thing. Yeah, that's fine. Okay. But why? Because MATLAB, we have the full license, university-wide license. You can install it on your laptop and work from home. Even you don't have to come all the I mean, to our computer lab. We have it also in our computer lab in the 5th floor. But as a student here at what university using your account, you can download it. MATLAB, the full version. This is extremely costly, expensive. Yeah, I mean, it's fine. I mean, my PhD student is working on both Python and MATLAB. Yeah, it's fine. Yeah, yeah, it's okay. All right. Excellent. So, course engagement and support. Some pre-recorded videos, which is available on Canvas, lecture slides, similar to what we have here. Course book, well-written and structured notes in chapter with tutorial questions and solutions. We have solved examples and tutorials. This is an excellent book. If you refer to it, that will be, I mean, enough to understand and acquire the required knowledge and achieve the learning outcomes. Timetable lecture, we have 3-hour slots, as you see today. Normally 2 hours lectures, new material, and the last hour, we keep it for problem solving and tutorial solutions together. Key dates, other extra reading, discussion boards, the video recording and lecture slides, all available on Canvas. Canvas is a virtual learning environment. Now, maybe you're going to ask yourself, how do I excel and get whatever I will get from this course and other courses? So normally, if we do the simple calculation, we have about 11 lectures, 3-hour slots, exam tutorial sessions, 27 hours, assignment questions. This is not with me, with you, but I'm dividing here the efforts you need to spend in order to get 150 hours. When 150 hours for the entire 14 weeks, starting from now until 16 December. I mean, if you think about it, weekly you need about 5 hours. So 2 hours plus these 3 hours, you are fine. You are in a good situation. Assignment questions, reading and private study, formal report assignment. So you need about 30 hours, maybe less. All right. Just this is tentative calculation, but revision time 15 hours and examination, which is only 2 hours. So total normally 150 hours. We say that if you spend 150 hours for any course, you will get an A distinction and understand it. I mean, some they spend less. I mean, it's comparable. Some they spend less than this because they attend the classes and get the majority of understanding from the lecturer. They don't have to go and do lots of reading later. Others, they don't attend the class and they have to spend double time and maybe they will struggle. So from my experience here in Heriot University and even in my previous university, University of Nottingham, there is a strong correlation between attendance and performance for students, right? Timetable, you know how to find the timetable? Okay, you can find it on just type timetable in Heriot University, and you can also, it's in your My Heriot account to see, I mean, the timetable. Now, course material and textbooks. There is no textbook required from you to buy, basically, all right? All material is found on Canvas. Notes organized in chapter headings and other items. So we have a chapter 1, chapter 2. So if you go and download everything and print it, you will have a fantastic textbook. All right, if you wish. I mean, download it. I have students, they downloaded it and they printed it and they keep it on their shelf because it's a very good reference. Just the teaching notes here, I mean, these chapters. The students who are unfamiliar or required to revise AC circuit analysis, for example, long time they didn't study, they are recommended to go electrical and electronic technology by HWUs. It is simple. Normally, this is designed for electrical, for students who want to revise and their background not electrical engineering, normally mechanical or chemical. It is easy and simple to follow. Right? We have it in our library in hard copy, and we have it also online in our library. Right? Students who wish to supplement their readings on electrical power engineering wish to obtain a copy of electrical machinery and power system. If you want more advanced, you are recommended. We have it also in our library by Stephen Chapman. Yeah, look at it. I mean, it's kind of old, but it's full of fundamentals. I studied this also I used this book 33 years ago when I studied electrical power systems. Yeah, others we have here also another textbook, Power System Analysis by McGraw-Hill, which is for Stevenson. That's also a very good book. You are not not necessary, but it's good if you want to get more knowledge. As I mentioned, the notes in the chapters are should be enough. I think you're looking here distracted. This electrical circuit analysis, I think this is for first year, which is something similar what we start. It's not mine, this is my colleague, I think, Dr. Munif. Yeah. Any question before we just provide an overview of electrical power system? Before that, because I mentioned I wanted you to have a look at Canvas. So this is Canvas. When you log in, as you see, okay, student. This is my Canvas normally in dashboard. So for the courses you are registered for, you should see them on your Canvas. All right. So look for the course. So this is electrical power systems. So what you will see as a student as the following. I wrote for you a welcome message. Did you receive it? Excellent. So here meet the course team who are lecturing. Yeah. As I mentioned, I am the global or senior course leader. You know the internet issue these days, right? Did you hear about it? The cable in the Red Sea being destroyed, so we're experiencing very slow internet. So these are pictures, are not opening. Yeah, here, this is myself. Dr. Jonathan is in Edinburgh, and Mr. Pang is in Malaysia. All right. If you move next here, this is the course handbook, which basically summarizes what we discussed just now. All right. If you look at the learning outcomes, as you see here, course aim, credits hour 15, learning outcomes. All right. These are the emails of the lecturers. Course assessment, as I mentioned. Resources, extra resources also. Textbooks, teaching material, and here the key dates. So here, week 4 release of the assignment report, week 5 time-limited online quiz, release on Friday, 10th of October. So the dates are there for you, okay? Available. Okay, what we're going to cover every week. And here, this is the second quiz in week 10. And the submission is in week 12 for the assignment. So you have 2 months to do it. It doesn't require 2 months. Maybe 1 week after you revise is more than enough, right? And the final exam will be in week 13 to 15, normally from 1st to 2nd to 16th of December, right? Leave student view because module. Yeah, here the key dates again available to you. All right. If you look, I'll just keep the student view for you so you are not confused. So these are the key dates, similar to what I showed you just now, by the way. Look here. What we cover every week and the release of assignment and also the online quizzes. This should be quiz 1, not a quiz 2. Right? Okay. Now what else we have here? If you go to module, declaration of authorship. This is a quiz, 3 questions. You have to answer it before you submit the assignments for all courses, by the way. Right? Once, you just do it once. Right? No grade, but you have to do it. No, it's not a grade, but you should do it. If you have any question about the assignment, you have to include it here. All right. Overview of assessment and feedback of this course. As you see here, detailed information, which I just covered. All right. All right. I even finalized assessment for distance learning students. Okay. This is the data sheet I mentioned. So you can download it, have a look at it. The question, it's not now, but yeah, I mean, as I mentioned, these two documents will be available to you during the exam together with the question paper. Okay. Excellent. And also we'll make the questions, some of past exam question papers available to you. Okay. Feedback, yeah, here, chapter 1. So whatever we are discussing, this is the first week, is available here, right? So this is the slides I presented just now, the first part. Everything is here for you to download, study from here. So again, notice that the second, yeah, here, because it's an overview introduction, and this is chapter 1 of the book I'm talking about, right? So two documents. One is the slides, and the other one is the chapter itself. So starting here, even the pages are numbered. So when you download them, chapter 1, chapter 2, chapter 3, you can make a textbook, nice textbook. Okay, if we go to module again, we have also some, I mean, if we go, this is because the introduction. If we start here from the AC circuit, same thing. We have the slides, which are going to show it to you after like 30 minutes from now. And we have multi-campus pre-recorded videos. It's good because it's meant to be for distance learning students, but you have access to them. Yeah, we recorded this some times ago. This, I mean, not all of them recorded by me. Other colleagues from Edinburgh and Malaysia, you will find the recording, all right? Available to you here. Excellent. So everything is on Canvas, and it's a well-structured course with all the notes, all the videos, etc. for you. This is if you need. If you attend the lecture maybe and go to the notes and the slides would be enough. Maybe you don't have to go and attend the watch the recording. But these recordings are brief. We don't want you to feel boring. I think each one is 25 minutes, 20 minutes, right? Any question? Yes? All good, excellent. Okay, now let's have an overview introduction about electrical power systems. What is this? This is showing the generation, transmission, and distribution of traditional power system. We have it here from starting from this point, generation. Now, generation, how we generate, normally the traditional way we have synchronous generators. Looking around here in UAE, how is the electricity generated? What is the primary source of energy? In the future, not now, in the future. No, the primary source, majority, almost 90% of the electricity here based on, no, natural gas. Exactly. We have synchronous generators, okay? We have solar, you are correct, but not that much, right? But as I mentioned, as of Vision 2050, is to have like more than 50% coming from solar. So synchronous generator here, right? Then what is this? Transformer. Transformer is doing what? normally stepping up the voltage, because when we need to do transmission here, we like to have a high voltage in order to minimize losses. So transmission, overhead lines, you find them a lot in the street. Then again, we have a step-down transformer, and here we have the distribution, another step-down transformer, and coming to our residential areas, right? So this is an illustrative block diagram. Normally, we don't keep it like this. We'd like to come out with equivalent circuit. The equivalent circuit, this is a generator. It has an impedance, Z. This is a transformer, right? It has also an impedance, ZT. This is the second transformer here, all right? Step down from 400 kilovolt to 11 kilovolt. Another ZD, which is the distribution impedance of the distribution part. And finally, here we have the load, right? Which is normally, as I mentioned, a motor. If you are an electrical power engineer working in a company like DEWA, for example, and you have a complicated power system, we don't present it like this. Instead, we present it in a single line diagram. Single line. So this is a generator, impedance. This is a symbol for transformer, right? Impedance, another transformer, impedance, transformer. So this is to illustrate this as a single line diagram. This is an equivalent circuit. Normally, what we use for analysis, something like this or like this. Normally, at the initial stage, we use the equivalent circuit because we can see everything, right? Here, when we become experts, we'll use the single line diagrams. We're going to cover all these things during the 12 weeks. So this is the traditional system. But what is the future grid? The future grid is going to be different. It's going to be smart grid. You told me about just now solar. The traditional way of generating, we are relying heavily on thermal power stations. As you mentioned, diesel generators, all using burning fossil fuel, whether it's gas, natural gas, or diesel, right? Or even petrol, right? This is changing. So we're going to have generation look from a wind farm, solar farm, hydro power as well. These are the thermal, as you see, nuclear, right? Factories to get this power as loads, houses, loads. Even our houses, we can be considered as a load and as a generator. We have solar panels. So this is what we call a distributed generation. So we are now, instead of having generation is only at one site, we are having it from different location, which we call it distributed generation. We need to manage it in such a way. We need to communicate, how to dispatch. It's not an easy task, but this is happening. So this is what we call it a smart grid. It's more complicated, all right? We're not covering it here, by the way, smart grid. You will shed some lights in other courses. When you study with me next semester, demand management and power system, we'll talk more in details about it, all right? But here, just to give you a flavor about the transformation from the classical or traditional grid to the smart grid, which is going to be more inclusive and interactive with the surrounding, because we are having generation from different location at different buses, for example, within the power system itself. Unlike currently, we have, as you see here, we have one location where we have generation. In a smart grid, you could have generation here, so you connected at this side, or at this side, or at this side, and so on, right? As you see here. Transmission and distribution losses efficiency. And when we come to transmission and distribution, just to give you an example, in UK transmission losses as of 2011, peak was 57 gigawatt, which is higher than now, by the way, right? 682 megawatt with 98.8 efficient. So transmission system in the UK is really efficient. How much is the losses? Is only 1.2%. But look at the amount of power we are losing. It's huge when compared to the total load. UK transmission transformers, also it's very efficient. 99.7 efficient. All these data, you can get them from national grid, right? We are going to study these efficiencies of the transmission system, distribution, and also transformers. These are fantastic results. Not everywhere they are having the same values. The transmission lines, as you see here, these are towers, and these are the transmission. Transmission lines are simple, right? We're talking about cables, but we'd like to find the equivalent circuit of these cables, right? We have here also the generator, which is normally synchronous generator, and we have also the load, which is normally induction motor. By the way, the generator and the motor, they are almost the same. In fact, they are the same. We call them an electric machine. The electric machine can either function as a generator or as a motor. It depends where you apply the power. If you apply mechanical power to this device, spin it, what is the output? Electrical. So what is this? The generator. If you apply electric power to the same device, it's going to turn, what is the output? Mechanical. So it's a motor. The motor input is electrical and the output is mechanical. Generator input is mechanical and output is electrical. Right? It's the same device. Electrical power system, this is the analysis what we are going to look. In electrical power system, we have a power. We have reactive power, we have real power, and apparent power. The real power is the power doing the actual work. Normally it's in watts, as you see here. Reactive power is required to create the magnetic field, which is important for transformers and motors to operate. And apparent power is the total of these two powers. We are going to look at it soon after we finish this introduction. What about this? What is this? Transformer. This is a schematic of a transformer. This is a magnetic core, coil. Simple, the transformer just turns and we have a magnetic core. We're going also to go through it as well, right? This is the calculation. Once we understand, we'll go and do the calculation to find the power flow. Voltage, current, power, everywhere across the power system. We simplify this by a single line diagram and an equivalent circuit, right? Yeah, this is what we showed you just now. Yeah, this is a simple three-phase system. The voltage shown are typical in the UK. When we say that these are the values, 22 kilovolt. We have three-phase generator, normally synchronous generator. Step up, the transformer A, we call it step up. Again, why need to step up the voltage? Reduce losses, exactly. I square R losses. When we step up the voltage, what will happen to the current? Step down, will reduce, all right? The current over here. And these are the generator, transformer, overhead lines, and so on. These are the symbols for transformers and generators and overhead lines, or could be just simple resistor and inductance. This is a typical, again, similar to what we showed you, but this is in South Australia, a three-phase, 50 hertz, 415 RMS line, and 24. This 24 volt RMS is the voltage we receive in our houses. Yeah, these are plugs. But normally coming to the universe like a three-phase system, 415. Right? So this is generator. So look, we have step-up transformer, and we have two transmission lines. One 275 and 130. Why? What do you think? What is the difference between them? Normally, we step up the voltage at a higher level for long distances. So here, 200 kilometer. By the way, if it's 400 kilometer or more than 300 kilometer, we'll step up this to about 400 kilovolt. because longer distance, you have to step it up in order to reduce the losses. Here, the distance is shorter, right? And so on. So typically, the generator, as we mentioned, it's a power station. Could be coal, natural gas. Yeah. Now, coal, everybody is trying to reduce coal because it is highly polluting our atmosphere, right? Induction machines, yeah, the motor, right? The traditional way of, as I mentioned, consuming electricity, we gave the example of AC, is three-phase induction motors, mainly is to consume the electricity as a load. But what about induction machines? Do we have induction generators? Just, yeah, induction machines, generator. By the way, most of the modern wind turbines, they are using something we call a doubly fed induction generator because it's more efficient, doubly fed induction generator used with modern wind machines to generate electricity, wind farms. It is more efficient and more reliable compared to synchronous generators. Because we cannot, why? Because the speed of wind, it's not constant. Synchronous generator, the rotor must be synchronized with the frequency, which means that you have to make sure that the speed of rotation is fixed. Here can vary. So we can control. This is something, yeah, I mean, a little bit advanced for research purposes. We're not going to touch doubly fed induction generator in this course. Just for your information, yeah, here, as you see, it is mainly in research area, basically to improve efficiency more than 50%, improve reliability more than 10 years, to increase compared to the traditional way of generating electricity using wind farms. So here, but in order to operate this doubly fed induction generator, we need power electronics. What is power electronics here? We need inverters, switches, and converters in order to control this machine to work as we wish with more efficiency. Even micro processors. We have other more efficient machines. We call it permanent magnet synchronous motors and generators. Sorry? You already were? Yeah, excellent. My PhD was almost 15, how many years ago? More than 18 years ago or 20 years ago, was based on permanent magnet synchronous motor, how to control it without using sensors or encoders. We call it sensorless control. My application was in semiconductor companies, not for doubly fed induction generator. Now the same motor is used in high performing electric vehicles because because it's very efficient and the volume to power ratio is smaller compared to other motors, or power to volume ratio is higher. Yeah. Okay. So yeah, these are efficient. Yeah, lots of research here using vector control and so on. Yeah. Yeah, it's very interesting. Sorry? Night, yeah, I mean, if you want to take the challenge, of course, at that time, as I said, almost 20 years ago when I did my PhD, it was something new. It was motivated by, as I mentioned, a company called On Semiconductor for manufacturing was having a problem all the time by adjusting the position. We're doing this XY table, yeah. So how to calculate, find the position, all right, without using the sensors, without the help of the operators to do some manual adjustment, by sending a signal, all right, high frequency signal injected, and calculate where is the position, and based on that, adjust the control, all right, signal to operate the entire system. Yeah, it was interesting. All right. Then induction, yeah, motor, what are the applications? Yeah, as I mentioned, induction motor is a lot used in heavy industry. Most of the factories using induction motors. AC systems here also using induction motors. We have transformers, as you see. These are transformers. We have a dry distributed transformer. You can find them. This is dry, air-cooled. And we have liquid-filled transformer, normally for high voltage. Inside, we have liquid for two purposes. What kind of liquid we have inside? Oil, cooling, yeah. We have oil for cooling purposes and for improving the dielectric properties, because you don't have arcing at high voltage to avoid breakdown. All right, so that's important for high voltage applications. Right, these physical things we are not going to we are not touching, but yeah, I'll keep mentioning about these things when we move on. Right. Traditional power grid, as I mentioned, main drivers for research and development. If you think about research cost, reduce capital operational cost, novel material and design here. Because if we think about, increasing the efficiency, reduce waste and losses, reliability, operational cost and availability. How to reduce waste and losses, for example, in transmission line, you have to use better material. In generator or transformer, how to make it more efficient. Where are the losses, by the way, in a transformer? You think about it, we that we have coil. Any coil, any wire, it has a resistance. And the losses normally, I square R losses. So if we reduce the resistance somehow, we can reduce the losses, correct, for the cables. Enhance material. Can we reduce the losses to 0% to 100%? Make the losses zero? Probably not. Well, yeah, it's difficult, but we can do that, by the way. But nothing is free. Theoretically speaking, you can do this. No. It is. Did you hear about superconducting materials? Yeah. We actually go to 100% efficiency. Almost, yeah. Yeah, almost. Maybe, yeah. Because if you cool down the material, for example, this cable, to a cutoff temperature, you make it superconducting. Superconducting means it doesn't have a resistance. That's the meaning of superconducting. All right? So no losses, basically. If no resistance, there is no, when we say superconducting. But how, as I said, nothing is free. You need to cool it down. To what? To minus 200 degrees Celsius. You need liquid nitrogen or so you have to get it somehow. All right. So, but yeah, we have superconducting for some application, by the way, when they do want. It's not only for the losses, because when there is losses, also the system will heat up. Normally, the losses will be dissipated as heat. You want to keep it safe also, all right? Not only about the losses. That's another important thing. A future power grid challenges, distributed renewable generation impact on the grid. That's very important. So this is demand management impact, voltage regulation impact, power quality impact. I have a PhD student who's currently working on these things and how to come out with energy storage options to mitigate these issues. Normally, when we have an increased penetration of renewable energy to the power grid, is going to be the same thing. What we have to do in order to make it more resilient and minimize the impact, because from renewable energy like solar, we don't have inertia for fault, for example. When we don't have the renewable energy generation, we need to come out with the storage. Remember, renewable energy penetration to the grid without storage is going to be very, very challenging. Why? Because you either have to install lots of these renewable, right, or you have to support it with energy storage. Batteries, pumped hydro storage, etc. So many flywheel, supercapacitors, and so on. Right? And we have to look at the power quality impact, which we're going to cover, give you an introduction in the last chapter. Right? These are some introduction. We try to address some of these, especially the last one, all right, when we move on, but not in detail. Right? I hope this provided you with an overview. We didn't start our course yet, but just to give you a flavor about what we are going to cover. All right? Any question? All good? Oops, where is it? What happened? Oh, we're not on Teams. It's somehow it is closed. Could be because of the connection, I suspect. Anyway, sorry? Still recording? Where? Oh, yeah, true. But it's not. Okay. Not sure what happened here. I think we just